Hello, my name is Nagasai Purvach and today we are going to talk about the decoder and its Verilog code in gate level modeling. The gate level modeling or in the Verilog, the most digital designs are done in higher level of abstraction like RTL. However, it becomes natural to build smaller deterministic circuits at lower level by using combinational elements such as and, or. The modeling done at this level is called gate level modeling, as it involves gates and has a one-to-one relationship between hardware and schematic and Verilog code. The Verilog supports a few basic logic gates such as primitives, as they can be initiated such as modules, and they are already predefined. Here, the gate level modeling is virtually the lowest level of abstraction used in switch level abstraction. It is rarely used. The gate level modeling is used to implement the lowest modules in a design such as multiplexer, full adder, etc. The Verilog has a gate primitives for all basic gates. Verilog supports built-in primitive gate modeling. The gates supported are multi-input, multi-output, tri-state and pull-up gates. The multi-input gates are AND, NAND, OR, NOR, XOR and XNOR, whose number of inputs are 2 or more, has only one output. The multi-output gates are buffer and NOT, whose output is 1 or more, has only one input. The language also supports modeling of tri-state gates, including buff 1, notif 0 and notif 1. These gates have one input and control signal and one output. The pull-up gates are pull up and pull down with single output only. The 2:. Now let us build a 2:4 decoder by using the gate level modeling. Before going on to the topic of building the 2:4 decoder, we have to know what is 2:4 decoder. The decoder is a combinational circuit which has n input signals and 2n output signals. For example, in 2:4 decoder we have 2 input signals and 4 output lines. In addition, we provide enable to the input to ensure the decoder is functioning. Whenever enable is 1 and it is turned off, then the enable is 0. The truth table, the logic diagram and the logic symbols are as given as we can see here. In the truth table, we have input and output. Here we are going to give only 2 input and output will be 2 into input, which is 4. So our inputs here are 0 0 0 1 1 0 1 1. For output of 1 1 1 0, we will be having input of 0 0. For the output of 1 1 0 1, the input will be 0 1. The output of 1 0 1 1, the input will be 0 1. The output of 0 1 1 1, the input will be 1 and 1. And we can see this is the logical diagram of 2:4 decoder. Here we can see 3 inputs. which enable A, B and 4 outputs, which are Y0, Y1, Y2, Y3, and this is the logical diagram or circuit diagram of the 2:4 decoder. Here we have A, B and enable as the inputs, and we are going to use NOT gates and NAND gates to make the 2:4 decoder. Here we can see the 1, 2, 3, 4 NAND gates are used here. The 4 NAND gates have 3 inputs and 1 output. The 3 inputs are as the 2:4 decoder's signal. We can see that the enable is connected to every NAND gate here, and the gate level modeling is used are the building blocks of the logical circuits. The Verilog basic gates are as primitive defines, and these primitives are initiated and created, and objects and get simply implemented by using module definition. The syntax of the logic gates which we can use are logic gate and object name and output port and input port. For example, NAND N1 Y X1 X2. We have to note that the logic gates are in lowercase and the object can be any name other than the keywords. In this above example, Y is output and X1 and X2 are the input signals. The Verilog code starts the module definition with input and output ports. The passed are the arguments. With the help of logical diagram, we shall initiate 4 NAND gates and 3 NOT gates to connect input and output signals to implement 2:4 decoder. Here let us go to the code of 2:4 decoder using gate level modeling. Here we are going to first declare the module name, which is 2:4 gate, which has 3 inputs and 1 output. Here we are going to declare what are outputs and inputs. We are going to declare the inputs are enable A and B, and the output will be Y, which is a array. And we are going to use a wire of EN, P, AN and PN. We are going to use the same level of connections here and create the NAND gates and NOT gates here. And we are going to see for the NOT gate, the input will be EN and output will be ENB, and input will be AN, and we are going to copy this and we are going to paste it here, and we are going to see it here clearly. And the NOT gate here is A and NA, and the NOT gate here is B and NB, and the NAND gates which are connected to the outputs as Y0, Y1, Y2, Y3, and which are inputs as EN, AN, NB. These, and we are going to write the end module to end the module which we have created, which is 2:4 decoder. And we are going to test the code. The testing of code is done in test bench. We are going to write module test bench, and we are going to give the inputs and outputs here, and we are going to initiate the design block decoder 2:4 gate by using initial. We are going to initial the test bench, and we are going to begin or write the code by using monitor. Monitor here is used to monitor the inputs and outputs with the reference of the truth table. With the reference of the truth table, we are going to provide input values. The input values are as follows: EN is 1, A is 1, BX, and we are going to use binary, so we are going to use bx here, which is 1. We are going to enable 0 a 0 b 0, enable 0 a 1 a 0 b 1, enable 0 a 1 b 0, enable 0 a 1 b 1. We are going to terminate the task by using finish tag, and we are going to end the test bench and end the module here. This will be the output for us, which is we have created VPP gate, and this is our signal diagram here. This is our signal diagram here. We can see the outputs are as 4 outputs for 3 inputs, and this is the schematic diagram which it is going to be created. And we can see here there are 4 AND gates and 2 NOT gates.